second part of stochastic process. Now, as I said, I'm working more on continuous process, which are called diffusion process, which are ruled by differential equations. And today, I'll continue a little bit with Ito's lemma, which is important, as you'll see, and mostly tell you what is Ito calculus. So Ito calculus is one type of doing calculus with stochastic processes. Then I will introduce briefly what is white noise. White noise is the most used noise term in physics. This comes, we can define it from the Wiener process, as you'll see. And last but not least, I will introduce the Fokker-Planck equation, which is a very important equation in stochastic process, which can be found as a limit of the master equation. So in a Markov process, you have the master equation, which I explained in my previous lectures. The Fokker-Planck equation is an equivalent equation also for the probability density, but for continuous process. So it's also very important. As you'll see, I will use it a lot in the biophysics modes that will come later. Right, so I stop sharing the screen. All right. So let me then start with a very important result in stochastic process, which is Ito's lemma. Well, I explain a little bit Ito's lemma. By the way, if you have any doubt, you can ask now. Please don't be shy, because now we are in the distance. It's good you make questions on the fly, even if you had doubts from the last lecture. If not, I will start with lecture 12. Lecture 12. Which I will continue with stochastic differential equations. And today I will go into Ito calculus, white noise, and if there is time, the Fokker-Planck equation. Fokker-Planck or Smolkowski. These are the contents of today's lecture. So let me first go with Ito calculus. I'll try to motivate this part, as usual, with an example. Give me a second, because I don't find my... Okay, so remember, when I was telling you on the other day, remember that in the general stochastic process, one has fluctuating time series, which is given by a certain stochastic differential equation, which in this case we will take something, well, let me go with an example. It's a process that is described by this equation, dt, and remember, now you have noise, plus g dB. Remember, this dB is the increment of the Brownian motion in a differential time, dt. Okay? Remember that this dB has this property, on average is 0. It has Gaussian distribution at all times, and remember also that dB squared equals to dt. So its square is not stochastic. Remember this. This is very important for the things I'm going to show you now. So imagine you have this process, and now you would like to calculate its square. As simple as taking x squared, no? So taking x squared should be something easy. So now I do the process y of t, which is x squared of t. This is t. And of course, if this is 0, y will be always positive, because I'm taking the square of a number. The square of a number is always positive. So I could do something like this. Okay, it will be positive. So now the question is, what is the equation? So now we have the process y, it is defined as x squared. And now the question I want to ask is, what is dy? Okay? It looks simple because it says, okay, of y, but dy will be 2x dx. No, this is what we learn in calculus. But you have to be very careful when you do this. I'll show you. Okay, so my goal is to have an equation similar to this, in which I have a deterministic part, and a noisy part, but for the process y. So let me go step by step. What is dy? So dy, by definition, is y at t plus dt minus y of t. Fine, you follow me, no? This. Remember, I could put dy parenthesis t, but I'm just simplifying this. Okay, I don't know if you see. Do you see my screen, my blackboard? Because there's not. I think that now it's better, no?
Yeah, now it's better.
Thank you. Okay, y at t plus dt minus y at t. So what is y at t plus dt? We have the definition here. So this is nothing but x squared t plus dt. I'm using the definition. And this is x squared t. Fine, no? So now we'll ask, what is x squared t plus dt? So x squared t plus dt is x at t plus dt to the square. So this is x plus dx squared. And the second is x squared. Okay? Remember, x at t plus dt is x plus dx. You follow me with this, no? So here I'm using the property that dx is x at t plus dt minus x at t. Okay? So x at t plus dt is dx plus, no, x plus dx. Okay? You follow me in this? If not, please let me know, because now it becomes a key point. You follow me?
I cannot see the one you wrote.
This one. Okay, I used the fact that dx, that is dx at t. Yeah? All this should have a t, but I am simplifying the notation. Okay, dx at t is the difference of x at t is x at t plus dt minus x at t. You agree with me?
Yes.
Okay. Then what comes here is x squared t plus dt. So x at t plus dt is x of t. I just move this to the right. Plus dx of t. Fine, no?
Yes, okay.
So now the square will be this to square. Fine? Which I write it like this. Okay? Fine?
I see. Okay.
Okay. So now it comes the key point. Now I'll make the square here. So what is the square? Is the square of the first square, the square of the second, plus twice the first times the second, no? Okay, agree with me?
Yes.
Simple and plain. And then this is minus x squared. Minus x squared. Okay, fine. So then I remove this with this. And I have 2x dx plus dx squared. Okay. Do you agree with me, no? All good.
Yes.
So now the typical thing would be, okay, so dy, because y is x squared, I would say dy should be 2x dx. That's calculus. That's what we learned in high school.
Yes.
Why do we do this in a differential equation? In a differential equation, if you have dx equals f dt, you put here dx and you have something linear with dt. But you put here dx to the square and you will have dt squared. And we say dt is small, so we remove the dt square because dt square is negligible with respect to dt. But now, look at this. We have dv. So if we put this here, there will be a term that when we square is of the order of dt. And this will survive. So we cannot neglect this term. Okay, because it's of the order dt. So now let me just continue. So here, I'll do 2. What is x? Okay, 2x. What is dx? So I'm going to use now this equation. Which I call 1. I use here equation 1. Dx is f dt plus g dv. dt plus g dv. Fine. And now I do dx squared. So what is dx squared? Is dt squared. So f squared dt squared, which we neglect. G squared dv squared. Dv squared dt. So it's g squared dt. Yeah, g squared dt. Plus dv times dt, which is of the order of dt 3/2. So all the rest that comes is of the order dt 3/2. So now becomes very, very important this term here. This is of the order dt. And the rest that we neglect is higher orders. Those higher orders we neglect, but this one we have to keep it. We have to keep it. So, this is very important. Because now, what we get, so remember, this is inito. So now what we get, you see there is this dt term and this dt term. So we get 2x, the 2x f plus g squared, very important this term, b squared dt plus 2x g dv. dv. Okay, this is the way dy changes. Okay, and this should be very important for you to notice, because here we don't use standard calculus. We are using another rule of calculus. This is really important, because you must see that in standard calculus, we would have done dy is 2x dx. Fine. This is what you learn in school. You do this, now you have 2 f dt plus g dv times x, 2x times this. So it would be 2fx dt plus 2xg 2dx dd. You see that when we do stochastic calculus, we have one more dt term. And this will be very, very, very important here. We cannot neglect this. We cannot neglect this. You see, because this will grow with time. When we integrate from time 0 to time t, this will grow with time. So, be very careful about it. So, one can generalize this and get a general formula, which I will give it to you now. General formula. So until now, I've done y, which is equal to x squared. But what if I get x cubed? What if I get e to the x? What if I want to do any, whatever change of variable for a stochastic process? For this, one must have a formula, a general formula for taking derivatives in ito calculus. Okay? The formula is as follows. So I will take now y will be y of xt. This will be any function. Any. Okay? I'm not a mathematician. Some functions will have pathologies, but in general, in physics we take exponentials, sines, cosines. These are functions that are well defined and don't have these rare problems. So, for any function, you would like to know what is the y, no? Okay, let's go with the general formula. So, this looks a bit difficult to remember, but there is an easy way to remember this calculation, and this is as follows. We have dy, and y depends on x and t. So one must say, okay, there should be partial derivative with respect to 1, dy1, okay. So there should be partial derivative of y with respect to t.
X.
dt, be careful. Partial y,
Yes.
dt, be careful. Then we say, okay, partial derivative of y with respect to x, dx. This would be standard calculus, but now we have to go one step more than standard calculus, that is adding 1/2 second derivative of y with respect to x squared dx squared. Okay? This is the general formula that you have to remember, which is often called Ito's lemma. So there are two formulas that people call Ito's lemma. One is the one I gave you the other day, which is dv squared equals dt. And this is another one you will find in many books. This is also called Ito's lemma, because it tells you how to take derivatives in a stochastic process.
So
Yes.
here you are for dy is not the total derivation.
Yeah. Here is the total derivation. So it's how much. So dy. Let me do a clarification.
I'm talking about the new relation, the general formula.
Here.
Because at the end you add you add something like error.
Sorry, can you speak a bit more clear? I couldn't understand.
I said at the end of this formula,
You
add 1/2 second derivative of y. Why this expression?
Second derivative y with respect to x squared dx squared. Because in general I must do this and continue till the end. Third derivative, fourth derivative, fifth derivative. I should continue. The reason why I put this is because this term will have a term proportional to dt. So it will be as important as this one. It will be as important as this one. I haven't given you the proof of this equation mathematically. I have given you the proof for one example, which is here. Here you see that the second derivative of y, it is important. You see that there is a term g squared dt. What is this g squared dt? So if you say y is equal x squared, first derivative of y with respect to x is 2x. So there should be 2x dx, which is here, you see, no? But the second derivative is 2 with respect to x squared. Second derivative is 2. So you put a 2 and a 2 here, 1/2, it cancels, and you have the term dx squared, which is what appears here in the formula. You see it, no?
Yes, but that means we are using the theory for the Taylor series.
It's a Taylor series, yeah, sure. It's a Taylor series.
Okay.
Okay. So I could continue infinitely, but the next term will be dx3, and this will be of larger orders of dt. So when dt goes to 0, they are negligible. So I will keep here terms that are dv's and order dt. Higher than dt, I kill them. They are negligible when dt is small. Okay?
Thank you.
You get the point? In reality, there should be infinite dt's. dt3, dt4, dt5. But I will only keep up to dt. This is the minimum. The minimum I should take care. Okay? Okay, so you see, if you apply this formula.
Professor, I also have a question.
Yes.
For this, the dy is explicitly dependent on a stochastic equation?
Yes.
Okay, thank
Yes.
you.
So y is the square of a stochastic process. Okay? It's not a deterministic quantity, so we cannot keep up to here. This would be standard calculus. You have a differential equation, you solve x, and then if you want to know x squared, you just do this calculation. This is for deterministic process, up to here. If x is stochastic, we have to add this term in the equation. Okay? So, I don't know if, well, maybe I can clarify this in this example and write it better. So if y is x squared, partial y with respect to t is 0, partial y with respect to x is 2x, second derivative is 2. So this formula implies that dy is 2x dx plus dx squared, which is t squared dt. Okay, which is what I had here, 2x dx plus dx. Okay, I can also write it dx squared. Okay. So this is standard calculus, and this is fully stochastic calculus. This will be 0, 0 for x deterministic. Okay. I hope this is clear, more or less. Okay. We can make an example, more complicated example, to show you the power of this calculus. The nice thing is that this formula can do a lot of things. I mean, you can compute derivatives of very complicated processes. Actually, people use this a lot in finance to make calculations, stock options, etc. So not only in physics and biology, but also finance. Interesting. So another example. This space. Another example that I think is interesting. It's a bit academic, but we'll get better ones when we go into the biological example. Could be if you think about a pendulum. You have a pendulum, you have a mass. G. This is the vertical, this is the angle theta. You could think about the motion of the angle. The motion of the angle, imagine this pendulum is in a fluid, and there is a friction coefficient gamma. Then one will have, this direction will have an equation of motion, which will be the following. This is mass times acceleration equals the friction times the velocity times the projection of the gravitational force along x, which is mg sine theta. This will be the equation of a pendulum, which you can see in classical mechanics. Interestingly, one could think about a limit where this is very small, so there are fluctuations. So imagine there are fluctuations, so then there will be noise, and we will say the mass is very small. So we will say this is almost equal to 0. So this is like stochastic pendulum. Pendulum in the overdamped regime. Overdamped.
Excuse me, what is the gamma factor? What is the gamma factor?
Gamma is the friction that the fluid is doing opposing the motion of the angle. Okay?
And in M we have mgs m theta.
Yeah, this is okay. This is mass times acceleration. This is Newton's law. Mass times acceleration is the sum of the forces. The first force is the friction times the velocity. This is the friction force. The second force is the projection in the x-axis of the gravitational force. Okay, because it's mg times sine theta. And this is the noise, so the force done by the fluid molecules.
I thought that it's SM, it's a sine. Yeah.
Okay, sorry.
Thank you.
Yes, this is sine. Sine of theta, okay? It's more clear, no? Okay, sorry. From the distance it's difficult.
No problem.
So, overdamped limit. So I will
And
say
the theta is the stochastic friction force.
this is the velocity. So theta.
No, zeta.
This is the noise. It's called white noise, which I will explain what it is soon. Okay, give me a second. Overdamped limit. So I'll say the mass is small. So I will get an equation that is something like this. Plus noise. This noise, and this will come next when I explain, is the derivative of B with respect to dt. So when you see this type of equations, and I will explain you this in more detail in a second, this has to be understood as, this is d theta dt, so this is mg sin theta dt plus dv. Has to be understood like this. Okay, this is dv dt, so when I put the dt on the right, it's dv. Okay, and even better we can do like this. So this has an amplitude, so we can do 2d dv. This will be when the g equals to square root of 2d. Okay, imagine this is your equation. This is the equation for the angle. You see the angle is doing oscillations, but it has also noise. Right? The angle will do, it has friction, oscillations, and noise. It will fluctuate the angle. So now imagine you want to know the equation for this. The projection of we are saying that the length this is equal to 1. So you would like to know an equation for the projection of the pendulum in the x-axis. This will be the sine. I would like to know an equation for sine of theta. You see that here I can show that this is a very powerful technique, because this equation, even without noise, you cannot solve it unless you do it numerically. This is an equation that doesn't have an analytical solution. It's very complicated. It's a non-linear equation, sine theta. So here you will see the power of using this equation, because I want to know the equation for this distance. Let me call it y. And now I just have to apply these rules. So what I do is as follows. Okay, I will need just derivative with respect to time, which doesn't exist. This is 0. This is partial derivative, remember. So this appears only when there is an explicit time dependence. There is no explicit time dependency here. Y depends on t, but through theta. So in this case, partial y with respect to t is 0. Okay, this is simple. Partial y with respect to theta is cosine of theta. Okay, the derivative of sine theta with respect to theta is the cosine. And you can see that the cosine, this is the sine, the cosine is 1 minus sin theta square root. No? You know this? Cosine square plus sine square is 1.
Yes.
Right, so, okay, so then,
Yes.
then this is 1 minus y squared. And next, if we do the second derivative, with respect to theta squared, is the derivative of cos theta, which is minus sine theta, which is minus y. Minus sine theta, which is minus y. Okay, so now dy is partial y with respect to theta, d theta plus 1/2 second derivative d theta squared. Okay, what is this? The first is partial y with respect to theta is square root of 1 minus y squared. D theta is this, you see,
Divided by gamma.
exactly, by gamma, so there will be a gamma factor, and d theta will be mg y dt plus square root 2d dt. Fine. And now 1/2 first second derivative, so it will be minus y halves d theta squared. Now what is d theta squared?
1 over gamma square and 1 over gamma square and
2d squared
Yeah.
as well. 2d, sorry, because you do the square of
2d plus mgy square.
No, be careful, be careful.
Dt is 0, so yeah.
D theta squared, there will be a dt squared that you kill,
Yeah, we can.
a
So
dv
we
squared
have only,
that you keep, and this times this that you kill.
yeah.
So then
We
this
have only 2d dt.
2d divided by gamma squared, dv squared, and this dt. That's it. And then you kill this, and you have it. So dy equals, okay, the terms dt are a bit complicated. So there is a square root 1 minus y squared gamma mg y minus d gamma squared y dt plus all the rest. Square root 1 minus y squared gamma square root 2d dB. This is it. So this is the way you will do an equation for dy, right? So it's more complicated than it looks, but you can get this from this simple rule. Okay. It's very important to see that now there is the force that depends on y here. The deterministic force depends on y, and the noise depends on y. So the noise depends on y. Depending where you are, you have more noise or less noise in the y value. This is also important. When you have this type of things, when g is g of a variable like x, this is the term that goes with dB. This is called multiplicative noise. Multiplicative noise. This is when the noise depends on the stochastic quantity. If not, it is called additive noise. Additive noise. Right? So I think I'll do a small break, and if you have any doubt, please ask me now. The next part I will explain what is exactly disk psi, which I call the white noise. This will be the next part of my lecture. But please ask me if you have any questions at this point. The best thing for this, as I always say, is you try to reproduce this on your own. You take a piece of paper without looking at my notes. You try to do one example, like this one, for example. And then you see. This will be, it's always the best to practice. Any questions?
Just at the end, when you define G equal Gx, if it be like this, we call it multiplicative noise, and otherwise additive noise. I couldn't understand what do you mean. What is that G equal Gx?
Okay, I give you an example. So when you have, for example, this equation. Okay.
We lost you, Professor, for a second.
No, okay, 1 second. So 1 would be, I don't know, minus x plus square root of 2d dB. Here, the noise, the amplitude of the noise doesn't depend on x. This is called additive noise. But if you have something like this, square root of, I don't know, 2, let me call it like this. This is when the diffusion coefficient depends on the position. This happens a lot in cells. So when you have a molecule in a cell, it's different the diffusion if you are close to the nucleus than if you are close to the membrane. So this approach makes sense, right? The cell is not a perfect aqueous medium that is the same everywhere. It is not. So one has D depends on X in general. In this case, okay, then there's the dB. This is called multiplicative noise. Multiplicative. And this is relevant in many biological situations. Okay, so this is a very good approximation for Brownian motion. So you have the particle, and all these surroundings are homogeneous. It's the same. The particle is here. The diffusion is the same here. Then if the particle is here, the diffusion is the same. This is more realistic in a cell. So in the nucleus, the molecules can move differently than when they are in the membrane.
Yeah, thank you.
Any questions? Okay, I will do a pause of 5 minutes and I see you in a bit. White noise. So I go to the second part of the lecture with the white noise. The fact that it's called white, it's something we could discuss in terms of the spectrum. It is white because when you go up to the spectrum of the noise, it has contributions of all the frequencies. And when you look at the light, it has different colors. You get white is when you sum different colors of the light. That's why it's called white, because it has influences or contributions from all the frequencies. But there are other noises that appear in the literature, like color noise, which is sometimes called red noise. There is also blue noise, pink noise. You'll find many around. Let me just go with the most used in physics, which is this one. So, just to motivate you, let me say that we write this, no? We write stochastic differential equation in this form. dx equals f dt plus g dt. Remember, f and g can depend on x and t in general. Okay? But physicists usually write physicists usually don't write this equation in this way, but they write it like this. X dot, so they divide by dt. And I also divide by dt because I'm also physicist. So G xa. Okay. Well, psi t times t is defined as dvt dt. So the derivative of b with respect to t. However, you should be thinking about what is this. This is dB. So dB dt is how much it changes b in a differential time interval, and this is dt. And so, however, you must think if this exists or not. And the reality is that this object doesn't exist. You can write it, but so no matter how small is delta t, small is a time step delta t, b of t will change randomly in one time step. So if you take the definition of this will be b at t plus dt minus b of t divided by delta t, and delta t going to 0. So when you make delta t going to 0 to 0 to 0, no matter how small you make this delta t, still this will change a differential amount. So you would have a small number divided by 0, and that's infinity. So the main point is that the binary process is b of t is continuous, but not differentiable. This is a mathematical statement that is important for you, that when you see this, you will see this in your next courses. You will see this when you read papers in biophysics. You will see this when you read papers in physics. You see this, you think about this, okay? because this is notation in reality. This doesn't exist with psi. It's notation. It means this. Okay. So how can I show you this? So if I do dv dt, this is a limit when, I don't know how to write this, we could say delta t. Delta t goes to 0 of b t plus delta t minus dt divided by delta t. Okay, this is the definition of the derivative. This is nothing but the limit when delta t goes to 0, delta b t, the change in the binary process in the time t divided by delta t. And the change of the binary process, this is of the order of square root delta t. And this is of the order delta t. So this goes like the limit when delta t goes to 0 of 1 divided by square root delta t. And when delta t goes to 0, this goes to infinity. So this is very pathological, I would say. So, alright. But this should be worrying for you. And what we can do later is to see something which is important, that is the autocorrelation function. Correlation function. So we can think about the following. It would be, for instance, what is psi t times psi t? This, as I said, both are delta v with divided by delta t. So this is the limit when delta t goes to 0 of delta b divided by delta t times delta b divided by delta t. So delta t is not stochastic, so then you can take it out. These averages are important, but they matter when the quantity is stochastic. So this is the limit when delta t goes to 0 of delta t squared, and here we put delta b squared. Delta b squared is delta t, remember. Limit when delta t goes to 0 of delta t divided by delta t squared, which is 1 divided by delta t, which is infinity. So even the correlation is infinity. However, because of the properties of Brownian motion, we have psi t plus tau, wherever is this tau, so tau greater than 0, this is 0. They are uncorrelated at different times. Okay. This is infinity and this is 0. So this is very strange. This is very strange. And however, there is a function that has these properties. So there is one function that is
Delta Dirac.
Delta Dirac, exactly, Delta Dirac. So Delta Dirac, this is t. It is 0 everywhere, except at 0, which is infinity. This is delta t. So this implies that this noise, when you do psi of t prime, is delta Dirac t minus t prime. Okay, this is the function, the delta is a function that has properties. But now I can give you a bit more insights about this result, and I can try to make a derivation.
Excuse me, the average of delta t is equal delta t, yeah?
Sure, because delta t is not stochastic. This is delta t. This is not stochastic.
And the upper line, the delta bt over delta t is considered as 1 over square root of delta t.
Yes.
How you did that?
This is okay. This is an order of magnitude. Okay, because delta b squared goes like delta t. Delta b squared. So delta b.
Yeah.
Okay. Delta
Yeah,
b
yeah,
goes
yeah.
like square root delta t.
Okay, yeah.
I will give you now more precise statements on this. Okay?
Yeah.
Let me try to clarify this with more precise math. So, in order to clarify, I'll say the following. Remember the Wiener process. The Wiener process has the following properties. So one is that it is Gaussian distributed. So B of t is distributed like a normal distribution with zero mean and variance t. So standard deviation square root of t. Okay, this is the standard deviation. The second is that B of t is Markovian. Which implies, remember that B of t is independent of whatever happened in the past, b t prime, or we could say t prime smaller than t. So whatever happens at time t, it happens only, so the jump that you do at t only depends on where you are at b of t. It's independent on the previous times. Okay, this is the definition of Markovian in continuous time. The third is that the increment of Wt is independent on its current value. So how much do I jump is independent on where I am. So the jumps are like random numbers, IID, so it doesn't matter. So it means that B of t plus delta t minus B of t, this is how much do I jump at time t, is independent of B of t. These are three properties that are important from the Wiener process. Okay, and so this means from the third property, from this one, from 3, we get that this is independent on B, so this means this B. Okay, this is for any delta t greater than 0, even very small. So independence means the following. I told you different times. This quantity B of t. So this times B of t. How much is this? It is independent. So if it is independent, what does it mean for an average? Please, you should know this. Okay.
For the first term, it must be independent, and for the second term, it must be dependent. Yeah?
Sure, you're right. But if x and y are independent, when you do the product,
It's the product of their.
it's the product of the averages, this, times y. And what is the average of y in this case? What is the average of b of t?
is 0.
0. So this is 0. Okay? Independence in this process, because average of BT is 0, it implies this. BT, okay? Fine. So independence means you can take an average and break it in the product of the averages. It implies this, which means what Said was saying. So this means that this property implies what Said was saying. We break it in two parts. B plus delta T times BT equals B square of T. Said was saying you can do this times this minus this times this. Yeah, sure. I agree, Said. But on top of that, that difference is 0. Because the difference is 0, you get this. Okay. And then, this we know. B square of T. What is B?
dt.
T. No.
T.
T. Because.
It's dB.
Okay. dB square is dt. But B square is T. Okay? T. This is one, like when you have a Brownian diffusion, x squared goes like 2 dt. But in the linear process, we remove this. Okay? Fine. So with this, we get the following. You see that when I do B T plus delta T times BT, I get T. So we can generalize and get that BT prime equals the minimum between T and T prime. You see this point? You see here you have BT and B, let me call this T prime. This T prime is greater than T. So what you get is the minimum between T prime and T here. See? I would change, I would get, if T prime would be smaller than T, I will have here T prime. That's why I write this. This is the minimum of T of T prime. If T is smaller than T prime, this is T. If T prime is smaller than T, this is T prime. Okay, so I have this equation. And now, what I'll do is, first of all, what I can do, is first see, I define psi of T like dB dt, and I see, first of all, that psi of T average is d of dt of B of T. Okay, but B of T is 0. So how much is this? Average of B of T is 0, right? Are you guys studying? Okay.
Yes.
Okay, this average is 0. So the derivative with respect to time of 0?
0.
0. Psi of the average is 0. And now if you want to know what is the autocorrelation, psi T prime, this will be nothing but d with respect to T, d with respect to T prime of BT prime. Okay, BT prime is the minimum. So when you make the derivative, what you get, you can find this in math books or do it, convince yourself. It will be d dt. And the derivative of this function, of the minimum, is the Heaviside function. It is theta of T prime minus T. can convince yourself that this is the case. And now you have to do the derivative of the theta function. Anyone knows what is the derivative of the theta function?
It's the Dirac function.
It's the Dirac delta, exactly. So this becomes Dirac. This is another way of making a proof of this. Okay, so this means that when people write this equation, of psi, often you have to write below this what is this psi, and when you read papers in physics or in biophysics, you see that they would say, all right, this psi is a Gaussian white noise, which means it has zero mean. So just after this equation, they write psi of t equals 0, zero mean. It is Gaussian distributed and it has autocorrelation, delta function. Delta t. And so we have this, and this Gaussian. This is the process. It's called Gaussian white. And you will find it in many books, physics, biology, finance, Gaussian process. Right? Any doubt? Questions? No questions? Alright, so if not, I'll try to give you an insight on the Fokker-Planck equation. Then we will be almost done with this part of stochastic process. So this is a very celebrated equation that is used and is useful to calculate properties of many trajectories. So what I explained you until now is to generate trajectories. So it's the dynamics of a stochastic trajectory. But so this is somehow the way, like when we said to do the Gillespie algorithm. This is one way of doing trajectories in a Markov process which is discrete. Here I'm talking about continuous Markov process. So the way you do trajectories is with this type of equations, which are stochastic differential equations. But then, as I explained, in Markov process there is the master equation. The master equation gives you what is the probability that many trajectories are at a given time in a given state. Okay? What is the probability of being here? There is a probability because some of the trajectories will be somewhere else. Sorry, most of them will be somewhere else. I'd like to know what is P. Probability to be at X at time T. Okay? And whether this equation obeys a given, so this quantity obeys a given equation, the quantity, this is for ensembles of trajectories. For this we need so-called Fokker-Planck equation. Sometimes explain that. Say Smolkowski, because possibly it was derived almost at the same time as Smolkowski. Okay, so I'll do is the following. It is a partial differential equation for the evolution of. It is a PDE of the evolution of T of xt. And I'm doing for x, but one can generalize for a process that has many dimensions. Okay, why it is a partial differential equation? Any of you can think about it? Well, it should be obvious because there is x and t, so there are two variables. Okay, it's not a differential equation; it's a partial differential equation. And it is useful to get, of course, stationary quantities, momenta like the average, the variance, etc. But it doesn't mean that this gives you all the information of a trajectory. It gives you the information of the trajectories at a given time. You won't get, with this type of equations, the information about, for example, how long it takes to reach a threshold, because this involves trajectories of different length. This trajectory has a different length than this one and this one. It is good for statistics at a given time. T. So let me try to show it. So my assumption would be that the only assumption is that we have a physical system described by this equation. Dx equals f t dt plus g of xt dv. Okay, so, well, first I make you a question. Did you learn this equation in another course? Because it could be what I'm telling you was explained to you.
No.
No? Okay. Fine. So my assumption would be I have a process that has this evolution, and f and g could be whatever. It could be that pendulum I told you. It could be a spring in a thermal bath. It could be, I don't know, pure Brownian motion, etc., etc., etc. This f and g can be anything. This is my only assumption. Now, what we will do is I will apply Ito's lemma. Ito's lemma to a function h of x. Okay, so we learned this in my class. So this means that dh, this depends only on x, not on t. H is the following, is dh dx times dx, dx is of this, f xt dt plus g xt dv. Okay, this is d of x. And then there is the plus 1/2 second derivative times the square of dx. The square of dx I will do g squared dt. Okay. This is dh. Okay, now I must confess you that when I learned this for the first time, it was not so easy. So I highly recommend you to take some time and review these lectures and try to do it on your own with paper and pen. Okay, this is dh, and I use Ito's lemma, but I'm taking total derivative. The reason I take total derivative is because h does not depend on t. Okay, it's just a function of x. But this is Ito's lemma, the same equation I used before. Now, what I'll do is to compute this quantity. So I'm taking the average of x, h. Remember, h depends on x, and x is stochastic. So then h is stochastic. I take the average, and I take its derivative with respect to time. What is this? So I take here dh dt. So I will divide by dt and take the average. So what will come out is, okay, first you can see the following. This will be, okay, dh dt. This will be f. This term. There is a dt, but I divide. So it disappears. Okay, this is one term. And I'm not putting the other term. This one. There will be a dv dt. But remember, this will be 0. This will be 0. Because dv dt is psi. So dv dt is here, dv dt is psi. And the average of psi is 0. Okay, so there is dht whatever times dv average is 0. That's why it doesn't appear here. In the next lecture, I'll give you more about this. This is called an Ito integral, but you can say the second term disappears because dv is 0 on average. And then we have the second term, which is 1/2 d squared h dx squared g squared xt. And the dt was cancelled by this. You follow me?
Yes.
Okay, maybe this is a bit tilting, but okay, you follow me live, this is good. Now, this looks a bit weird, this average, but we can write the average explicitly. So in reality, I would say that x is in R, so it's a real number. It can take any value from -infinity to +infinity. So this is nothing but the following quantity. All this is the integral. When you do this average, you have to average over x. Remember, t is not stochastic. You have to average over x, and x goes in R. So you have to go from -infinity to +infinity. There will be a dx, it will come, of all this, which is f xt dh dx plus d squared xt to second derivative. And now, okay, I'm averaging. What does this average mean? It means that I am averaging with a probability distribution, right? When I average, for example, when I average x, this is the integral of dx x px. There is a distribution. The distribution now is the distribution of the process, so it's p of xt dx. Okay, so something to remember is that what I'm writing here, these brackets, in this context, means you take the integral from -infinity to +infinity of to average with this probability distribution pxt dx. Okay, this is what the average means, and the rest that I'm putting is what I have. All right, so now this looks complicated, but you see that I have fp h prime. I can use now the so-called, okay, I don't remember how this is called in English, but it's a change of variable. When you have u, okay, I learned this in Spanish, so please, apologies, but minus integral of ddu. You remember this rule, no?
Integral by parts.
Integral by parts, okay. I remember the math, but not the not the name, okay. And when you have this from minus infinity to plus infinity, you do this minus infinity, plus infinity, minus infinity, plus infinity, and you will see that there will be terms. The first will be fp h prime, so we will have fp here, but we will evaluate p in minus infinity and plus infinity. And I will say that p in plus infinity and minus infinity is 0, because the distribution is not, it cannot have a value in infinity. So in this step, I will say that p in plus minus infinity is 0. Okay, it's a good assumption, I would say, no? So in that case, I can change this by the following. It will be integral minus infinity plus infinity. H will not be with derivative, it will be like this. And then there will be the derivative with a minus of, so it will be partial with respect to x of fp. So it will be f xt p 60. Okay, this will be one term that will appear. Okay, and then there is the second term in which I can apply this integration by parts. Thank you for the name. Integration. I didn't even remember the name in Spanish, so it's good you tell me. Integration by parts. I apply twice, and I assume that this and also this one. So please check at home. The derivative is 0 at the borders. And this becomes 1/2 of partial derivative. Second, here there are two derivatives because I did integration by part twice, of g squared xt pxt close bracket dx. Okay.
Actually, I don't understand why there is a minus in the first partial derivative.
Why? Because I did integration by parts. And when you
Yes,
integration,
but we make the minus out of the integral. No, before.
It is here a minus. Because, okay.
No, but there is another, it's equal. Okay. The other equal, I thought it's minus.
Equal. Equal.
Okay,
Fine.
okay. It's
Fine.
fine.
There was one integration by parts from here to here. And
Yes.
two integrations by parts from here to here.
Yeah.
Right. So now this looks a very complicated equation, and it is. Not be honest. So I forgot one part in my proof. Let's see if I find it. Sorry, there's a small problem. Okay, so this is the change of the average as function of time. Now we continue the proof on the other side of the blackboard. Actually, the last part is the simplest, so it's the one I remember. But just in case. Okay, so this is, we have this equation on one side. On this. Okay. And now I will do the calculation of the same quantity from a different path. So I'll say what is 8. What is average? So again, what is average 8? I told you what is making an average here. So making an average, nothing but integral minus infinity to infinity dx pxt and 8. That's it. So now, if I take the derivative with respect to t, what is this? I should take the derivative of all these objects. What should I do? Okay, so I'm me write it explicitly. X, hx, or pxt, hx. Okay. You had a course of mathematics, so probably it should be easy.
It is only the derivative of P
Sure, because
multiplied by H.
this doesn't depend on t.
Yes.
This is the only thing that depends on t.
Yeah,
So
it's the only.
it's integral minus infinity to plus infinity dx
Dx, dPE.
partial p xt with respect to t times h of x. Fine. So now, given this, we have two equations for the same quantity. This one, and this one, right? So this must hold. This is true. This holds for any h of x. So this is equal to this for any h of x. What does it mean? It means that the integrands, what is inside, are equal. This integral is equal to this integral for any function. It means this equals to all this. It means that the derivative, I take this with respect to t, equals all this that I have there, minus, as a derivative with respect to x, f 16 dxt plus 1/2 second derivative. Second derivative squared t squared t p xt. And this is what is called Fokker-Tam equation. Okay. This is right. The derivative of the distribution with respect to t has one term which contains this part, is the drift, and a second term that contains this part, which is the noise. Again, to memorize this, the first goes with a minus and with one derivative. The second goes with a plus, second derivative, a 2, and a square. It's not that difficult, this operation. Yeah. Just to give you one example to finish the lecture, you could think, I don't know, for example, remember I told you about Brownian motion. So Brownian motion, pure Brownian motion, f is 0, and g is the square root of 2d. So Brownian motion, one-dimensional Brownian motion. Remember, in this case we have f equals to 0. We say fxt equals to 0. And g xt equals to square root of 2d. Okay, very simple. Brownian motion is very simple. There will be more difficult process than this. With this 0 and this square root of 2d. If I apply the equation, this one, what I get is this is 0, so out, and g squared is 2d, right? This is g. G squared is 2d. 2d divided by 2 is d. So for this process, you have second derivative of p xt with respect to t equals d second derivative of p xt with respect to the square. Which is, I showed you this some lectures ago. This is called the diffusion equation. If you solve this, you get a Gaussian. You get a Gaussian distribution, which is nice. Of course, we can do other examples. We can check in other classes. You can put here a spring and here noise, and then you won't get a Gaussian distribution. You will get a more complicated Fokker-Planck and a different equation, right? But this is a very important equation in physics, and maybe I can give you another good example. Let me add one more example in here, which is an epsilon variation.
So the purpose of this equation is to know the distribution of the process we are studying.
Yes, exactly. The distribution at any time t. Okay, because this is pxt. If you solve this equation, you know the distribution at any time. Okay. Another example is, for example, when you have a particle in a fluid and there is a force field. There's a force applied to the particle that depends on the position of the particle, which is x. And the particle has diffusivity d. So in this example, you write something like this: dx is mu fx dt plus square root of 2d dB. Mu is 1 over gamma, the friction coefficient. So this is a very small variation with respect to Brownian motion. But now we have a force field. Okay, this could be, for example, x. If it's x, it will be like a linear potential. If you put minus x, it will be like a spring. Put here x, minus x, for example, it will be a spring. But it could be whatever. So if you have this equation, you come here, and you apply the same equation. This is the nice thing of having general equations. So this will be partial p. Okay, partial p xt with respect to t equals the mu is constant, so it will go out. So it will be minus mu partial with respect to x of x dxt plus 2d squared, it will be a d second derivative. D partial 2 with respect to the square of p xt. This will be Fokker-Planck for this problem. If you go to Wikipedia, you will find this one. But this doesn't mean it's the most general. And then one can do this in 3D and so on. So instead of derivatives, one will get gradients and so on. But I think for you, learning this is already very good. Okay, so this is kind of the master equation for continuous processes. And it's relevant, as you see, if you can solve this, you know the distribution at any time. And I will use this in some biophysical examples later in the course. And for now, this is it for today. So any doubt or question? You see there's math, but this math will be useful for you.
I want to ask, for the part where you said chi is Gaussian, and then so that's why it is a Gaussian white noise. Can you repeat why is it Gaussian?
Yes, because it is Gaussian because B is Gaussian. So the derivative of a Gaussian is a Gaussian because B is constructed as the sum of Gaussian increments. So how much psi is the change of B in a small time? And B is changing by Gaussian increments. As I explained to you in the previous class or two lectures ago, B of t is just a process in which you are summing Gaussian random numbers. So psi of t, which is the change of B, is also Gaussian because the increment of is a Gaussian, and psi is the increment of B. So then it's a Gaussian. Remember in the previous class, I don't know in the previous or 2 lectures ago, I defined the distribution of dB. You remember, no? I think it was 2 lectures ago. dB, I tell you, has a Gaussian distribution. You got this, no? Rewind, take the notes and go back. Go back, go back, go back. And 2 lectures ago, I said that one has E of dB equals E minus dB squared divided by 2 dt. Okay, something like this. But, okay, I told you this. Do you remember? You understand? Yes?
Okay.
Please say, because if not, I don't hear. I don't see you here. So yes, say yes, clear. Okay, this was the distribution of dB. But psi is dB dt. So dt is not stochastic. So the distribution of psi is the same as the distribution of dt at the end. Sorry, of dB.
Okay, Professor.
You get? Okay. It's a good question, eh? It's a good question. And remember again that the b is the sum, or the limit, when delta t goes to 0 of delta b's. So in the end, b is nothing but integral of db's. And each of these dB is a Gaussian random variable. Okay. Other questions? Any questions?
I have a question.
Okay.
For h, are there any assumptions for the function h?
Well, it's no. In reality, it's a real function. It doesn't have singularities, so it doesn't have infinities, and yeah. So whenever p goes to 0, h is positive. Okay, or h is finite when p goes. So when h goes to when x goes to plus minus infinity, h is finite. When it means it can be 0.
Okay.
Other questions? No? Okay. Very good. So we then stop here.